Welcome again. We are going to continue with the session. And our next speaker is Professor Alayn. Professor Alayn is a professor at the Public University of Navarra in the Electrical, Electronic and Communications Engineering Department. He's also member of the Institute of Smart Cities, and he's an IEEE senior member. His research interests are in the fiber optic sensors and optical fiber communications field. And in the last decade, his focus of research has been mainly on distributed optical fiber sensors, particularly those based on measurand and Rarity scattering effects. This research has led to numerous scientific publications in international scientific journals and conferences, and he has also published 4 book chapters and supervised 7 doctoral theses on these topics. He's also the inventor of 2 international patents related to distribute measurand sensors that are currently licensed. In addition, he has also participated in many research projects and also industrial R&D projects with companies. So, Professor Alayn.
Well, thank you, Carlos. Well, they have asked me to give the talk in English, so I'll proceed to do so. Well, today I'm going to talk to you about distributed fiber optic sensors and their applications. So I want to start by discussing what is the interest of these sensors. And for that, I'm going to show you several catastrophes that could have been avoided if the sensors that I'm going to introduce today had been in use. For instance, you may remember the collapse of a bridge in Italy several years ago due to the failure of a tendon that led to 43 people death and an economic impact estimated in more than 2,000 million euros. Also, the fires in California from time to time. This is the Camp wildfire that started when a high voltage power line that was overheated really got to touch the branches of a trees and initiated a fire that produced 86 fatalities, more than 19,000 buildings and construction destroyed, and made the local electric company file for bankruptcy because of the demands that it had to face. Also in Mexico, a year later, explosion of a pipeline due to an undetected leakage. And there are more almost every year. Last year in Mexico, the collapse of a bridge in the metro. Just 1 month ago, the collapse of a pedestrian bridge in India with 135 deaths. And even the recent sabotage of the Nord Stream pipeline, this probably could have not been avoided with the sensors, but it could have been detected earlier than it was. And even apart from these very impacting events, we have a situation nowadays in which almost every day there are structures that fail, that are damaged, and that damage is not detected. And in time, this leads to a really high cost in terms of maintenance and repairing. So let's see what role can play distributed fiber optic sensors to prevent this. So in this talk, I'm going to give a very brief introduction to this sensor technology, discussing the concept, the advantage, a bit about the physical fundamentals, and also the performance parameter. And then I'll describe some applications in which we have been directly involved to give an idea of what they can do. Well, distributed fiber optic sensor. This is the schematic view of the sensor. Is made of an optical fiber. Okay, so optical fiber similar to the fibers that are used for communications to bring internet access to your homes. But this optical fiber is going to become a transducer. So every point of the fiber is going to become a transducer, a sensor. And this fiber is going to be installed or fixed to a structure, the structure to be monitored. And the fiber is going to be also connected to the interrogator, that is the electronic instrument that generates and processes the optical signals that are launched into the fiber. So the optical signals that propagate in the fiber experience changes in their characteristics, and these changes are detected by the interrogator, and from those changes, the physical magnitude that is measured can be obtained. We will see that in a second. For instance, if it is a distributed temperature sensor, what we get is a distribution of the measurement is a distribution of the temperature along the fiber. So we see that we get temperature information in all positions of the fiber. It's like having a large number of thermometers, one after the other. And if we have, for instance, a hot spot, we detect that. And if we have a cold spot, we detect that. We measure that, and we localize very precisely where is situated. The same with the strain sensing. Strain sensing, the fiber is fixed to the structure, and so it experiences the same deformation that the structure is experiencing. And we get a measurement of the distribution of the strain that is experiencing the fiber along its length. So we get areas where there is elongation and also areas with compression. Or we can also measure the other big three type of distributed fiber optic sensor for vibration measurements. Vibration measurements, these sensors are able to detect very small vibrations that reach the fiber. They're able to localize them in position and to quantify this amount of vibration. So what is the advantage of these sensors? Well, particularly compared with traditional sensors. The first advantage is the small size of the fiber. The fiber is like a human hair, and with the coverings, it can be up to a few millimeters, but it's much smaller than the equivalent electrical sensors. For instance, strain gauges are small, but the cables that you need to feed those strain gauges, really, if you need a lot of sensors, it start to be really a bulky scenario. So another very important advantage is that the fiber is dielectric. The fiber is immune to electromagnetic interference. It's chemically passive. And also very important is that the fiber has very low attenuation. So you can have really very long lengths of fiber that are interrogated, and you get long distance measurements. Another big advantage, monitor everywhere. If you have traditional point sensors that you install in a structure, you locate those sensors, and you need to be lucky to detect damage. If damage does not take place close to where you have located your sensors, it simply is not detected. In contrast, by using distributed fiber optic sensors, you can really have a dense mesh of optical fiber, of sensing fiber, that covers the whole structure, so no area remains unmonitored. And monitor everything. There are multiple applications. This is a figure taken from the company AP Sensing, and this shows areas of application of distributed fiber optic sensors in the railway network. And for that, they use the fibers that are already installed in that railways. Along the railways, there are fibers that are used for communications, but those fibers can be used also for sensing. So with these fibers, for instance, we can detect trespassing, people that is getting close to the railway. And this is done by detecting the vibrations that their steps generate when they get closer. You can also detect fire along the tunnels by measuring the temperature. You can detect the positions of the trains along the lines by the vibrations that they generate when they pass along. Or you can monitor the electric power cables, detecting hot spots, or even natural hazards like landslide that may affect the railways can be also detected with these fibers by vibration, for instance, induced when there is the light. So many things that can be done with this type of sensors. The fundamentals, how they work. Well, I don't want to go a lot into the details of this. Just mention that these distributed fiber optic sensors are based on effects of light scattering, that is interaction of light with matter, with the material of the fiber. And there are three main types of this scattering. You have Rayleigh scattering, Brillouin scattering, and Raman scattering. In Rayleigh scattering, you have that the light interacts with small variations in the density of the fiber. In Brillouin, the interaction is with acoustic waves that propagates in the material. And in Raman, the interaction is with molecular vibrations of the material itself. But as I said, I don't want to go into the microscopic view of these effects. I want to have the view of the engineer that is really using these sensors. So let's describe, for instance, how the sensors based on Brillouin scattering work. So in the Brillouin time domain analysis sensors, what you have is an optical fiber, and you introduce a PAM wave in one end of the fiber, and in the other end, you introduce a probe wave. So the PAM wave generates what is called a Brillouin gain spectrum, so a range of frequency at which the probe wave that is counterpropagating experience gain. And this Brillouin gain is generated at a frequency separated from the PAM by a parameter that is called the Brillouin frequency shift. And it turns out that this parameter depends on the strain and the temperature that the fiber is experiencing. So if we measure this frequency shift, we can obtain a strain or temperature. And we want to get like a distributed measurement. So what you do is you pulse the pump, you launch pulses into the fiber, and at the same time, you measure the gain that the probe is experiencing along the fiber, in all positions of the fiber. So you get a measurement. If you repeat this measurement by scanning the probe frequency, what you get is distributed measurements of all the gain spectra along the fiber. So if you then work out what is the peak of this gain spectra, you can obtain the Brillouin frequency shift. And from the Brillouin frequency shift, you can work out either the strain or the temperature that is the fiber is subjected to. So to implement this, you need a setup in which there is lasers, pulse generators, optical amplifiers, detectors, and a number of other electronic components. Is a box like this size, like the picture here. That is one of our prototypes. And with this, you can interrogate. That would be the interrogator. Okay. The performance parameters of these sensors. The main parameters are four. Is the precision of the measurement, the range, that is the length of fiber that you can measure, the measurement time, and also the spatial resolution. Spatial resolution is how many points, independent measurement points you get along the fiber. And that is directly related to the duration of the pulse. And these parameters are not really independent. So there are trade-offs among them. For instance, if you increase the length of fiber, what you get is higher attenuation. So your signal is smaller, closer to the noise, and then the measurement precision is reduced. If you want to increase the measurement precision, what you can do is repeat the measurements and average the results so as to remove noise. And then you get improved precision, but the measurement time is increased. Similarly, you can increase the spatial resolution, but that is going to lead to the range, the measurement time, and the measurement precision probably being suffering, because what you need to do to increase the spatial resolution is to reduce the duration of the pulse And that means like a reduced interaction and a smaller signal. And again, that is closer, you get less signal to noise ratio, and all the other parameters suffer. So you need to really, when you are designing a system, you need to optimize these parameters depending on your needs. Well, really, our research here in the university, what it does is to try to improve these parameters, these performance parameters, as much as possible. So during time, what we have done is to develop different measurement techniques that I'm not going to discuss, and this has led to a number of papers in conferences and scientific journals. And what is more important for us even is two European patents that are currently licensed and in exploitation. So there is transfer of technology to companies, really. Just to give an example of the sort of things that we are able to do with these sensors. We have developed techniques to be able to measure dynamically. So that is, as it's shown in this video, we are applying load to a structure, and this structure has fiber fixed to it, these white lines. And what we are seeing is in real time the strain associated to the flexion and the torsion in the fiber. So in fact, with our technique, we're able to measure in kilometer range fibers. We are able to measure with 20 centimeter spatial resolution and with a frequency of measurements of around 700 hertz. So 700 times per second, we are able to measure in 1 kilometer like 5,000 points simultaneously, strain in 5,000 points. Okay? In the other opposite range of the length spectrum, we have also worked in very long length measurements, and we have developed techniques to measure up to 200 kilometers with 2 meters spatial resolution and achieving 2 degrees precision. So we are able to measure 100,000. We have 100,000 thermometers at the same time along this length. And that is very useful, for instance, if you introduce a fiber in a high voltage power line, to be able to detect all along the line possible hotspots that indicate that there is issues in the line. Or if you place that fiber along a gas pipeline and you want to detect leakage, because leakage changes the local temperature along the pipe. The other type of sensors in which we have worked is based on Rarity scattering. And in this case, as I mentioned before, what we have is that light is reflected by microscopic variations of density and refractive index. So if we launch a pulse into the fiber, what we get is a very small reflection for every position in the fiber. And we are able to measure with very high precision the amplitude and the phase of the optical field that is being reflecting from the fiber. So we can use that for sensing. There are several methods. The methods that we have developed is based on measuring the optical phase. What we do is we measure the difference in phase between the optical signal reflecting from 2 nearby positions, say a few meters, 1 or 2 meters. And this difference in phase is proportional to the propagation constant of the optical field and to the length, to the difference in length of these positions. So that we are able to detect very small changes in length in the fiber. In fact, we can measure this phase with a precision of 1/10 of a radian. And this leads to us to be able to measure changes in, say, in 1 meter in length of the order of 1 nanometer, of nanometer order. So we have extremely high precision there. And that leads us to have a very sensitive sensor for vibration. So any vibration that gets to the fiber and modifies slightly the length due to compression or elongation is going to be detected, as we will see later in the application. So let's see what we can use this for. Let's show some examples of application of the sensor for structural health monitoring. First, in civil engineering structures. Well, before really going to full projects, going to the real world and measuring with these sensors, you need to analyze in great detail the installation of the fiber, how you fix the fiber to your structure, because that is critical to obtain good measurements, particularly for strain measurements, because you want that the strain, that the loads that are experienced by the structures are really transferred to the optical fiber, because that is where you measure it. So what we did when we started with this was to buy a number of concrete beams and really experiment with fixing the fiber to the beams with different methods, with different fiber types, with different epoxies, glues, mortar, and then testing the beams in testing rigs that are here in the mechanical engineering department. And so we measure with our sensors to see what was the strain distribution and the displacement, and we compare that to independent measurements to find out what was the best method to really install the fiber. So this is really quite important and quite time consuming. Another issue that you need to take into account is how you are going to place the fibers, because you are measuring a strain, but by measuring a strain, if you locate the fibers in a smart way, you can measure a lot of things. For instance, you can measure curvature, you can measure by integrating deflection, displacement, you can measure torsion if you place the fibers with a 40-degree angle to the axis of the structure. And if you know the material of the structure, you can work out what are the torsional moments or the flexural moments, and have a good idea of the loads that are being experienced by the structure. So with this knowledge, we started to go for projects and do things. This is one of the first things we did, is the monitoring of a hydroelectric water channel. These water channels are used by electric companies to generate electricity. And what they do is they divert water from a river. In this case, it was the Rarity River. And this is taken to a channel and then to a small hydroelectric central where they have a turbine, and there they generate electricity. And in Spain, there is hundreds of kilometers of these channels. So here, the company that was involved in this project wanted to really investigate the structural integrity, to ensure the structural integrity of these channels, because as you can imagine, if one of these breaks, it can be a very serious stuff. So what we did is to take advantage of the fact that in these channels, they already had like fiber optics for telecom. So what we did is to use branches of fiber from this network and install a fiber sensing cable that was embedded in the structure itself. These are some pictures of the installation. We see that what we did is to cut slots in the structure, introduce the fiber, and then apply some mortar to fix the fiber to the structure. And then from a remote location, we were able to monitor in time the evolution of deformations in areas that were tricky, and ensure that there were no problems in the structure. Another example in which we were involved is a tunnel of the high-speed train in Alicante, actually, in which during the construction they wanted to really assess the distortion of the sections of the tunnel. So what we did was to install fiber in the arcs of the tunnel, and we just have here the installation. And here, what we did was to measure strain in days, and then by integration, being able to calculate the distortion of the section of the tunnel, again to ensure that there were no issues during the construction. We have done other projects like that. For instance, also in the Yesa Dam, we did some demonstration of the technology, measuring the settlement of the crest of the new dam, the dam after renovation. And all these projects were with measuring strain, but we have also done measuring temperature. For instance, we developed a system for water leak detection in the Nagore Dam, that is in the Itoitz Reservoir. And this dam, during the construction of this dam, an optical fiber was laid all along the axis of the dam at a given height, and this fiber was next to the core of the dam, the asphaltic core that makes it really watertight. So this fiber that was installed was a special cable. It's a cable that not only had optical fibers but also electrical conductors, and these conductors were used really for heating. So current was introduced in these conductors that generate heat, and we studied the evolution of the temperature in the cable with time using the distributed fiber optic sensors. So as we know the theory, this temporal thermal response of the system leads us to really measure the thermal conductivity. We know the theory, and we can measure the thermal conductivity of the soil around the cable. So with that, we can detect the presence of water, because a dry soil has a much lower thermal conductivity than a soil in which there is water flowing. So, for instance, these are example measurements. This is conductivity measured in a particular day along the 600 meters of the dam. We see that we see it like a constant conductivity, more or less. This corresponds to the dry soil. And these are measurements in another day in which we saw that suddenly there was a peak there in conductivity, increased peak in conductivity that made us thought that there was water there. And when we saw this, as you can imagine, we really got very worried, because it's difficult to pick up the phone and call someone and tell them that their dam is leaking. So before doing that, we investigated that in detail, what was happening here. And it turned out that really the water that we were seeing, it was because this is a very rainy day, and it was water really flowing down the slope of the mountain. It was not a leak, but it was water that was reaching the cable in this area. That is the area that we were measuring, and it was coming from the mountain. So it was completely normal, and it was good because this demonstrated that the system worked. So it was useful at the end. Well, I don't want to go. I don't know how I'm doing with time, but we have been involved in other projects, also in measuring structures, not civil engineering structures, but more like engineering structures. For instance, in solar trackers. Solar trackers are these metallic structures where the photovoltaic panels are mounted in solar centrals. And we did a project with a company to study the effects of wind on these trackers that can be really harmful. So for that, we fix fiber to the beams, and we monitor in time the deformation, and we correlated that information with the wind that was present in the area, so that they could figure out how to improve their designs. And we have also done these sort of things also for wind turbines, for blades, for structural testing of wind turbines. Cannot give a lot of details about this, but it's more or less the same ideas. So all this about applications in the field of structural health monitoring, but there are also applications of distributed fiber optic sensors in smart cities scenarios. For instance, we are currently now involved in a project that deals with the monitoring of traffic in roads using optical fiber, distributed optical fiber sensing. So the objective of this project is to be able to do what is shown in this video. We want to be able to locate precisely every vehicle that is in the road. We want to know the velocities. We want to be able to differentiate between different vehicles because of the weight of the vehicle. We want to be able to detect traffic jams, accidents. So it gives a lot of possibilities. So how this system operates, the idea is simple in principle. The idea is that when you have a car going along a road, this generates like a seismic wave, like a vibration wave, and this vibration reaches an optical fiber. The good thing here is that the optical fiber is already in place. The optical fibers are for communications are typically laid along cables, and in Navarra we have a lot of them. You may have seen the blue lines in the side of the roads. You have optical fiber there, optical fiber cables there for telecommunications, but we can also connect to those fibers and use them for sensing. So this is what we have done. We have connected our prototype interrogators for distributed acoustic sensing, vibration sensing. This provides measurements, and as we are going to see, with some signal processing and machine learning, it provides really actionable information to traffic and road management people. We have the good thing is that we have the collaboration of the Navarra governments that have provided access to its network, and Navarra government has more than 700 kilometers of optical fibers along the roads in Navarra. And currently we are working in a 40-kilometer link that goes from Pamplona all the way to the town of Aoiz. I'm going to show you some real measurements. This is just a section of this 40-kilometer link. This is about a kilometer, 2 kilometers or so. But keep in mind that we are measuring at the simultaneously the 40 kilometers. So what we did was to place a camera here in this roundabout, and you are watching in this video the view in that direction. And this trace that you have here is the response of the sensor that we have superimposed into the map of the area. So okay. So you can see here these perturbations that you see are actually the vibration that is picked by the fiber that is here on the side of the road. You can see here it's buried there, it's all along. And this perturbation, this is the cars that are moving along the fiber. For instance, this big one that is moving our way is this truck, this big truck that is there. You have also the cars that follow the truck, so that we are seeing in real time all along the 40 kilometers, all the vibration, the distributed vibration picked by the fiber. Okay. So, and we see both directions because the sensitivity of the sensor is enough to pick also the cars that are going in the other direction, and even in multiple lane roads, you can measure that. I'm going to rush. This is the same measurement, but displaying in the x-axis the distance, and this is time. And we have here each of these trajectories is the different cars that are being detected, so we can count the cars, we can work the slope. By the slope, we can work the speed of the cars, the distance. We can detect cars that stop. We can differentiate even between cars and trucks, for instance, because you see that the amount of perturbation is different. In fact, we have fed these measurements into a machine learning algorithm to be able to differentiate between motorbikes, cars, and trucks. And we train this neural network, and really the accuracy with real traffic that we are getting is quite good. And we are even working on this to improve it. Just the conclusions. The idea, what I wanted to give you is that distributed fiber optic sensors can be really useful for assessing the health of structures, and they can be also useful for many other things, such as for smart cities, traffic monitoring, as we have seen. And there is plenty of work to be done. So we are hiring. In fact, we have an opening for hiring people, and it will be compatible with master's final project. So if you're interested, come and talk to me. Okay. Sorry for the length of the